Hello everyone and welcome. So to kick us off, I'll briefly introduce the company. Atacama is the data trust company. So we focus on a wide range of data challenges so you don't have to. And our goal is to ensure data is accurate, accessible, and actionable for our customers. Our customers are usually large enterprises, and we help with various initiatives such as data preparation for AI, machine learning workloads, data analytics, Customer 360, and much more. So why did we decide to build a SaaS product in the first place? Well, first and foremost, we want to be agile, so we want to respond to market needs, innovate, and deliver the solution rapidly. Then second of all is the economy of scale, so everybody wants to have higher margins, and so do we. With that is connected operational efficiency, so we want to automate as much as possible, and we want to grow and scale with the number of tenants or customers effortlessly. Last but not least, we want to reduce the cycle time, so we want to be receiving feedback from customers fast, also from our internal engineers, and act on this feedback. So we started in early 2024 with our SaaS adoption. We quickly realized there is no blueprint for SaaS. So it's very individual to your company's needs. And for us, the case was that we had a lot of single-tenant applications, and we wanted to build multi-tenant applications and break up some applications from monoliths to microservices. We also formed platform engineering teams, which I'm part of, to help build foundational components for the SaaS, and we'll talk about that later. So there is no blueprint for SaaS, but you can use some patterns to help you along the way. So in this talk, we'll explore on the management side, the provisioning. On the application side, we have isolation. Application side is usually what people imagine when you say SaaS. So these are all the components that make up your product. And last but not least, you have tenants. Well, hopefully you have tenants coming into your platform, and you need to onboard them somehow and also give access to their internal users so they can use your product. So you have some idea how to build a SaaS application, but you also have some external inputs. So usually from the business, you have some goals, like why you're building SaaS in the first place, some success criteria, but also some limitations, such as when you need to deliver the solution, or some legacy considerations, such as needing to modernize some services along the way. One of the biggest challenges for us was tenant isolation. Since we work with a lot of sensitive data, our clients are usually banks, insurance companies, etc. So it's very important to keep the tenant boundary. There are several patterns that you can use to enforce this segregation layer. In the previous product generation, we started with the full stack isolation model. So this is a very simple model. You deploy all your applications in a single tenant manner. And usually the isolation boundary is something like AWS account, Kubernetes cluster, or a VPC. So this works well until you have a lot of customers and a lot of things to manage. At that point, you can look at resource level isolation. So now you can deploy single tenant and multi-tenant applications and move the boundary to the resources themselves. So, for example, when you provision a dedicated database for the customer, you control access to that database on the database level. If you're coming in from the other side, where you started building multi-tenant applications and have multi-tenant data stores, you will usually find that in such cases, you put all your data into tables, which contain some discriminator columns, such as tenant ID, that you filter on, and this is called item-level isolation. To give you maybe more context for what the business goals were for us, from the management side, we wanted to lower onboarding time, so meaning that we decrease time to value. When the customer buys the product, they should be able to use it rapidly. We also want to increase operational efficiency, meaning that there is no manual toil, everything is automated. And last but not least, we want to have a secure solution that is compliant even for the most demanding customers. We also have some lessons learned from the previous product generation. So our engineering department was familiar with Helm and Kubernetes. So these are things that worked well. They are familiar with these technologies. And we also learned that they don't want to manage infrastructure. They want to build applications. So they want to create applications in the domain of their expertise. They don't want to take care of databases or some other solutions. So this is where the platform engineering team comes in and provides some building blocks that the teams can build on top of. And we'll cover some in this presentation. And we want to be open for multi-cloud in the future, since our previous product generation runs on AWS and Azure as well. So here's a quick overview of the building blocks we provide to the teams and the architecture of the solution. We start with an EKS cluster or a Kubernetes cluster, which is provisioned by the infrastructure team. Then the platform engineering team comes in and provisions some static resources. So you need networking for connectivity. You also need some IAM roles, some IAM policies. And we use GitLab provider in Terraform to bundle the outputs of these Terraform modules and share them with the Helm charts as Helm values. And we'll see that later in the presentation. From the platform engineering point of view, the building blocks we provide to our feature teams or application teams are on the control plane side databases. So each tenant gets their dedicated database cluster, object storage. Each tenant gets their dedicated S3 bucket, and Keycloak, where each tenant has their own realm. We also have messaging, or we introduced RabbitMQ into the mix, as we have combination of single tenant and multi-tenant components, and we have some applications that are still being broken up from monolithical services, so this should help them achieve their goal faster. Then we have also the application plane, right? That's where the products actually live, that's where the business applications are, and we need to bridge the infrastructure with the applications. So we built two dedicated Spring Boot services in Kotlin. The first one is called Tenant Context and is responsible for credentials handling and routing information, along with upholding the resource isolation. And we also have a Key Vault service, which is responsible for managing sensitive data that the customers might input and handles all the encryption and decryption operations. Last but not least, we need to deploy Keycloak itself. And I'll pause here. On the previous slide, you might have seen some icons. So if you could please raise your hand if you are familiar with Terraform or used it before. Okay, that's like 95%. Nice. What about Crossplane? Has anyone heard of it before? Okay, that's like 20%. So for the rest, I'll try to give a quick summary. I think tomorrow there's also a dedicated session on Crossplane itself. So if you're familiar with Terraform, you usually create some modules that have some opinionated inputs. In Crossplane, this is defined as a Kubernetes custom resource definition. So it's defined in YAML. It's not defined in HCL. And here is a snippet from our case where we use Amazon Aurora as our database cluster of choice. But if you're familiar with Terraform, something needs to happen in the module. Otherwise, it's kind of useless. So usually the module has some resources that are backed by various providers. So there is a similar concept in Crossplane, where the providers actually run in your Kubernetes cluster and are responsible for talking to various external APIs and provisioning the resources. The module content that you would have in Terraform is defined by something called composition pipeline in Crossplane, which is again some definition of Kubernetes resources that need to be provisioned. So for example, in this case of provisioning database clusters, you end up with some Aurora instance and some KMS key for encryption. So let's have a look at how that looks like in practice. So we have the same snippet from before. This is the way we provision database clusters. There is some composition pipeline that runs in the cluster, and this is something that you get out of it. So here is a view of all the resources that get provisioned. So for example, we have resources that are managed by the AWS provider. We have some resources that are managed by SQL provider, and we have some resources that are managed by Kubernetes provider. So I'll pause here as it's a pretty loaded concept, and we could spend a lot of time on Crossplane itself. And here I would like to highlight some provider usage and some Crossplane function usage in our organization. We mostly build things on AWS. So we use a lot of AWS providers from the AWS family. We also use Keycloak provider. We do some HashiCorp Vault things. And we also use SQL provider as we run Postgres. And we also use Kubernetes provider as kind of supplemental functionality that Crossplane providers might not offer yet. So this allows us to use providers that are operators that are Kubernetes aware, such as external secrets or the official RabbitMQ operator for cases where such functionality doesn't exist in Crossplane. So for example, there is no native RabbitMQ provider in Crossplane, but we can use the Kubernetes provider to kind of bridge this gap. So let's have a look at some practical examples. Our first business goal was to decrease time to value. So in practice, this means that, again, no manual actions should be performed. Everything should be automated. We would like to leverage Terraform for static infrastructure provisioning and Crossplane and ArgoCD for dynamic infrastructure provisioning. So I prepared a little case study on the database clusters. And the flow is as follows. So customer comes into our cloud portal. You can kind of imagine it as AWS console. They click create environment. That kicks off a GitLab CI pipeline, which generates Helm values with some information about the tenants and some metadata. And these Helm values are passed to Helm charts. So in this case, some database clusters Helm chart, which contains the Aurora claim or the opinionated YAML snippet I've shown earlier. But in order to provision the database cluster, you need to know to what AWS account you're provisioning it into, what region, and some other inputs. So we take these values from the Terraform outputs, and using the GitOps pattern, we commit some additional set of Helm values that also get fed into the Helm chart. Then we run another GitLab pipeline, which basically renders the Helm chart into plain Kubernetes manifests. And we have ArgoCD watching these target GitOps repos and reconciling the state. In the Kubernetes cluster, we run Crossplane, which then picks up the claim that has been submitted and does its magic. So here's the composition pipeline that runs. We provision AWS-specific resources to get a working database cluster. So we need some key for encryption, we need some configuration, we need the cluster definition, and we also need to know, for example, how many reader instances the cluster should have. And the AWS providers in Crossplane are responsible for provisioning the infrastructure on the cloud provider side. So we end up with an Aurora instance and some KMS key. We then also take the super user or the master user password and transform it a little bit so it's projected into Kubernetes as a secret. So then it can get fed into Crossplane SQL provider, which provisions some Postgres-specific resources that we need for other use cases. So for example, you might set up some extensions, some roles, and some grants. So with this, we achieved automation. We no longer need to schedule installations. We also reduced error rate as we have standardized a lot of things, and we get continuous drift detection and fleet-wide upgrades for free by using Crossplane, as it's always reconciling the resources in the background. Continuing on the topic of increasing operational efficiency, it's not only about removing manual actions or manual toil, but also about removing unnecessary coordination. So in the previous product generation, we had a 6-week-long release cycle where it meant that all the components are released at the same time. This caused a lot of friction, and the configuration was centralized. So there was a lot of back and forth between the product engineering teams and cloud engineering teams when the configuration would, for example, change. So in the SaaS product, we decided that the deployment should be decoupled, meaning every team or every component can be deployed at any time. And in order to do so, we needed to decentralize the configuration. For this, we opted to use Crossplane claims again as some opinionated CRD or some opinionated schema our application engineers can use. So to switch things up, I'll use messaging as example. We provision a RabbitMQ broker. It's a very similar concept as was shown for the database clusters. But we also allow the product engineers or the application developers to claim some resources or to configure the broker. So you need a user to be able to connect to the RabbitMQ broker, and you also need exchanges, queues, and bindings between them to be able to consume and send messages. So using the same pattern as before, we run our rollout pipeline, which templates the Helm charts into plain Kubernetes manifests, commits them into the target GitOps repo, and ArgoCD watches these applications and these repos and reconciles the state. So here's an example of what happens when you claim a user. We use the Crossplane Kubernetes provider in this case to generate some initial password for the user using external secrets operator. We store this password to AWS Secrets Manager, and we use the official RabbitMQ operator, again wrapped by the Crossplane Kubernetes provider, to provision the user within the RabbitMQ broker. So we also found out that this pattern actually generalizes pretty well. So instead of having various repos where there is shared ownership, we settled on one common repo where the application owners define their components and describe them. From that repo, we generate a bunch of ArgoCD applications, and our application engineers are able to define these cross-plane claims for configuration in their Helm charts. So it might look something like this. If you use Helm for templating, we run the rollout, meaning we do something like Helm template and commit the output into a GitOps repo. So now you have a plain old Kubernetes manifest that the ArgoCD running in the respective clusters can watch. So with this, we achieved complete decoupling of the configuration, enabling self-service at scale for our teams. So we are no longer the bottleneck. We don't need to review a bunch of merge requests. The teams are self-sufficient, as they can just edit their Helm chart at any time and deploy at any time. So here's a quick summary of all the resources we provide in our building blocks. And this was the key enabler to achieve decoupled deployment and allow teams to decompose some of their monolithical services without having cloud engineers interfere or be the bottleneck. So at this point, we went over how you provision some resources. So for example, database clusters or message brokers. We also saw how you can in self-service manner configure these resources, how you can provision users to access these resources, and you might be asking, like, how does this work at runtime? How do your applications get access to these users? How does multi-tenancy fit in? How does it work? So I prepared an example of accessing data stores and message broker. So in the previous example, we saw how you can deploy a RabbitMQ user, and we'll have a look at what you can do with that user. So again, we use a similar pattern where we bridge the static and dynamic world. The static world is from the Terraform. We generate some Helm values, for example, containing the account ID, the region, and some identifiers that are needed for this to work. And we also take the dynamic values generated from tenants coming in or being updated in the platform. And we pass these Helm values to a Helm chart. In this case, the service is tenant context service, which, among other things, defines in its Helm chart deployment and service account. So now we have some pods running in a Kubernetes cluster. We also have applications running in this cluster as well. So these are your product applications that want to perform some work, and they want to be able to access the RabbitMQ broker. So these applications in their Helm chart define the claim from the self-service section, and the tenant context service uses Kubernetes API to watch these resources. So as these claims come in, the tenant context service watches these based on some label. And when the application pods want to get the tenant context or want to access the RabbitMQ broker using the user they have defined, they issue a request against the TCS, and that does several things. So first, we need to authenticate the request. So for that, we use the Kubernetes JWTs with some audience defined. And we also need to evaluate the permissions. For example, if the component that is multi-tenant and is running in some namespace and serving some set of tenants can request this context, and whether it's not requesting context of another tenant that it might not be serving. So there is some permission level check at this stage as well. And the tenant context service fetches the secret. So for example, it would be RabbitMQ user's password from some secret storage. So for example, from AWS Secrets Manager, from HashiCorp Vault, or even from plain old Kubernetes secret. And then it returns these secrets along with the full context back to the application that's requesting it. And then the application can use this, for example, to access the broker or connect to the database and do some meaningful work. So we also found out that this pattern of using the Kubernetes watch and doing some permission check and validating the access works rather well. We also use it for service discovery. So we have a mix of single tenant and multi-tenant components that need to know in what other namespaces or what are the addresses of other components' namespaces to be able to talk to them. So we wouldn't watch, in this case, some user claim from RabbitMQ. We would watch the Kubernetes kind service that has some specific label, and then tenant context service is able to create the routing information and pass it along to the client. So the application pod can talk to other application pods. There's no prior knowledge in what namespace, for example, the other component might live. Yeah, so I just marked them with 1 and 2, so it's visible. There will be also a PDF export of the slides. And I will not go over this example, but we use a similar approach for sensitive data access and encryption. So the pattern is generalized for service discovery and routing, which I have covered by watching the services using Kubernetes API. We can also access data stores and message brokers, so this was shown on the 2 slides back. And for accessing sensitive information and performing encryption, we use similar pattern, just in a different service called Key Vault. So if you remember the architecture overview, that was the second service that we have written in Spring Boot that facilitates all of this for our clients or from the application pods. What I would like to also emphasize here is that this was something that worked for us, right? There is no silver bullet solution. There is no blueprint. So in our case, we had prior knowledge of Spring Boot. We were, let's say, more versed in writing applications than being the traditional DevOps guys. But for example, in the context of your company, similar pattern can be achieved by, for example, using HashiCorp Vault sidecars or provisioning some AWS-specific role for each component so it can fetch the secrets directly, for example, from Secrets Manager or Parameter Store or whatever other secret store that you might have. So coming to the final section, I would like to share some lessons learned and recap the presentation. So what I would like you to take away from this presentation is you should think about the deployment and isolation model. Like, is it worth even to provision resources in dynamic way? Can you get away with using the full isolation pattern and having everything single tenant? That's up to you to decide and think about. At some point, you will be probably implementing also some application plane components as you need to interconnect the infrastructure that you have provisioned on the control plane side with your customers, which are the application engineers or the product engineers. And if you work in an organization that's larger or don't want to become a bottleneck, you should also think about self-service at some point. So it doesn't matter what technology you pick. Like we chose Crossplane, but you can use Terraform, OpenTofu, CDK, like whatever you're familiar with and whatever works for your use case. And sharing some takeaways from around 16 months usage of Crossplane, I think it works very well for the self-service approach. So if you serve a larger amount of teams, like 10 plus or even 15 teams, you don't want to be the bottleneck. You want to give the teams autonomy so they can self-service themselves. I think it also works really well if you have some prior experience with Terraform or you have some resources which don't change that often. So for example, networking or clusters, you can provision these using Terraform and use the GitOps patterns to pass some values back to the dynamic world, for example, by templating Helm charts. And if you use Crossplane, you get continuous drift detection and reconciliation for free, as the providers are running in your cluster as controllers or operators and always doing their thing. However, there are also some downsides. So the learning curve is steep. So now you need to be familiar with how Kubernetes operators and controllers work. You also need to be familiar with the Crossplane providers and some of their quirks. And I think you should also invest more into end-to-end testing. So if you use tools like Cattle, Chainsaw, or whatever thing to end-to-end test Kubernetes manifests, then that comes in handy. And again, it's an additional tool in your tool stack. So if you like to keep things simple, maybe think about just sticking to one tool. At the end, I would like to show some lessons learned and maybe share some fails that we have encountered along the way. So we realized that performing disaster recovery is now more complex. You have something running in the background, always trying to reconcile any drift that might occur. Fortunately, you can pause this reconciliation in Crossplane, perform your disaster recovery procedure, and then enable it back. You also need to be aware of the Kubernetes resource lifecycle. So when you submit some resource to the Kubernetes API server that is then deleted, for example, you make a mistake in your Helm chart and suddenly there are no manifests, Argo prunes everything, you don't want to end up in a situation where your customers' databases are now gone. Hopefully you have backed them up. We didn't initially in our dev environments and were surprised by this behavior. There is an escape hatch, so you can use orphan on delete approach where you specifically request that any resource that gets deleted from the Kubernetes API doesn't get deleted from the cloud provider's API, for example. But then you need to end up, or you need to create some mechanism that will clean this garbage or perform some tenant offboarding. And also what worked for us really well is empowering your engineers to experiment. So even though they're familiar with Helm and Kubernetes, these are still some new concepts for them. So we created a tool to provision local clusters using K3D, where they can try out all this self-service configuration as if it were deployed to production before deploying to dev environments or staging environments. And at the end, I would like to highlight, I think, one of the key takeaways. There is no silver bullet solution. So think what works the best in your organization, and hopefully you have learned something along the way. Thank you.
Thank you. Great presentation. I will have two questions so far. One is actually two questions in one. What is the scale number of customer environments and whether you did migrate from previous product generation?
Okay, I'm not sure if I can share answer to the first question, but currently the thing I talked about is previous product generation. We still run it. Like that's the thing that makes money. There is still active development. So we didn't migrate any customer to the product, to the new product. I think the strategy there is to get new customers on the new product. We didn't really think about the migration yet.
Thank you. And the second question is how to implement the fair multi-tenant queue and schedule jobs.
Oof, I think this is a very loaded question, so I might need some specifics. I don't know if it's discussing the RabbitMQ I have mentioned. I'm not sure who raised the question, but feel free to stop me after the presentation and we can discuss the specifics. I don't know what technology the question is about.
Fair enough, thank you. And one more question is there. If I understand correctly, devs provide configuration in Git and GitLab CI. Have you considered using some internal developer platform like Backstage instead?
Right, I think this is a very good question. So, yes, our engineers define all the configuration as Kubernetes manifest, so they commit that to Git, and we run GitLab to generate the resulting manifests. The question about using internal or IDP, something like Backstage or the alternatives, is I think interesting one. So we wanted to use GitOps as much as possible. I'm not really familiar with all the IDPs out there, but we don't want engineers doing any sort of like ClickOpsing in some web UI. Maybe you can also set up IDPs in a way that it's GitOps friendly, but we wanted to start out simple and just keep all things in Git and maybe introduce some IDP at a later stage. We didn't really have a need for it at this moment.